Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we're going to be looking at the topic sulfur and its compounds. So, today we are going to be looking at sulfuric 6 acid and basically the contact process. So, the contact process is the large scale manufacture of sulfuric 6 acid. You take a deep dive in each and every step in that process. So, and then this will bring us to the end of the session. So, sulfuric 6 acid is usually manufactured by a process called the contact process. So, the first thing you notice with industrial process, we always start with the raw materials. So, we have done other industrial process, you can go back and check them out. We have done the solvay process in Form 2. We have done the fractional distillation of liquefied air in Form 3 and Form 1. We have also done the ABA process in nitrogen and its compounds. And today we are looking at now the contact process. Forms part of paper 2 in chemistry. So make sure you are able to see those steps one by one. So the raw materials for the reactions are sulfur. This sulfur 4 oxide is gotten from the sulfide ores or sulfur. So we said when we were starting the topic on sulfur and its compounds that sulfur can be extracted by fresh process, which is also an industrial process where sulfur is having deposits deep into the earth. So they dig and then extract that sulfur. We looked at that process, you can go and check out. Other sulfur compounds, as other ways that sulfur can be extracted is in their combined state, and we call them the sulfur ores. And so these sulfur ores are usually heated and we get the sulfur oxide we want. So another raw material is water. You need water. We need air, which will be containing the active part, which is oxygen, and also concentrated sulfuric acid, which is going to be used. So the first step in the reaction is the production of sulfur oxide. So sulfur oxide is produced by either burning the metal ores that we talked about or burning sulfur in air. So, for example, if you burn sulfur in air, you form sulfur oxide. Other metal ores are the sulfide, like the iron sulfide. If you burn it, you form the sulfur oxide and iron oxide. So, obtaining the sulfur oxide from the pyrites is cheaper than from sulfur itself. So, flowers of sulfur from pyrites is impure and contain dust. So, which can involve incur extra expense and time for purification. So the next step is purification, and purification and dry is all about the catalyst that we'll use. We do not want to have those impurities as we move on because they are going to interfere with the reaction. So sulfur oxide and excess air are passed through a series of dryers and purifiers. This removes dust particles which would poison the catalyst. So you can see the main reason we are removing or we are passing it through the dryers and purifiers is to remove anything that might poison the catalyst. So what happens is that they take up the surface of the catalyst, which impairs its efficiency. We know that the reactions are occurring on the surface of the catalyst. So if another compound occupies that space, it means that what was supposed to react was not going to react efficiently. So purification is done by electrostatic precipitation, and drying is done by passing it through drying agents like concentrated sulfuric acid. And then after that, the third step is the reactions. The products are taken to the heat exchanger. So we have dry sulfur oxide and dry air, and pure sulfur oxide and pure air. So these are taken to the heat exchanger. In the heat exchanger, the mixtures are heated, and when they are heated, the temperatures increase steadily and they increase to around 450 degrees Celsius. After that, the reactions are taken to the catalytic chamber. And remember, we are also following the flowchart on the side, so make sure you are following. We are at the heat exchanger, so we are going where the reactions are moving to the catalytic chamber. So in the catalytic chamber, we have vanadium 5 oxide catalyst. We are going to see why vanadium 5 oxide is preferred. So in the catalyst, sulfur 4 oxide reacts with oxygen to form sulfur 6 oxide, and a lot of heat is produced. This reaction occurs at least at 450 degrees Celsius, and it is exothermic in nature. We'll see how we can be able to maximize this. So the product is sulfur 6 oxide, and it is accompanied by release of heat. So because there's a lot of heat that is being released in this reaction, we need to remove that excess heat. So for us to get good yield of sulfur 6 oxide, first of all, we need to get optimum conditions. And these optimum conditions we are talking about, first of it is temperature. And since the forward reaction or the reaction of formation of sulfur 6 is exothermic in nature, it would be good to have this reaction occur in low temperatures because the reaction already is producing more heat. We do not want to pump more heat in this reaction. But low temperatures usually lower the time at which the reactions reach at equilibrium. So we usually fall under like an optimum condition because the high temperatures as well helps to make the sulfur 6 oxide to decompose. You don't want it to decompose and you don't want it to be very slow. So an optimum condition of about 450 degrees Celsius is usually used. It's very reasonable and it's not that expensive. Another condition is pressure. High pressures usually favor production of sulfur oxide. This is because the volume of gaseous reactant is higher than the volume of the gaseous products. So increasing the pressure will enable like the forward reaction to occur better. So this involves reduction in volume. So pressure used should be high to give it like an economic convenience. But high pressures are very disadvantaged in that they are very expensive. They're very expensive to generate and to maintain. So it uses a lot of costs. So high pressure also can liquefy the sulfur 6 oxide produced. So what they do is they come to a certain optimum pressure, an optimum pressure that is required so that we can be able to convert most of the reactions. So also another condition that is required is a catalyst. A catalyst can help to allow the reactants to reach equilibrium faster, or it increases the rate of reaction. So it merely speeds up the reaction and it reduces the time it takes to react to equilibrium. So the main catalyst is vanadium 5 oxide. It is spread out in silica gel to increase surface area for combination of reactants. And dust settled in the catalyst may reduce its effective area. Dust also may cause the catalyst to be poisoned, further reducing its efficiency. So that's the reason why we had to purify the gases thoroughly. An effective catalyst is also a platinized asbestos, can be used as an alternative, but we prefer vanadium 5 oxide because it is not easily poisoned and then it's cheaper and readily available. Remember, this is a large scale process, so minimizing the cost is also one of the things they consider. So the highest yield of sulfur 6 oxide is obtained at optimum conditions of 450. You need to remember these conditions: 450 degrees Celsius and a pressure of 2 to 3 atmospheres. It needs to be in presence of vanadium 5 oxide. So those are the optimum conditions. So finally, step 5, remember we were in the catalytic chamber. So we said that heat is being produced a lot in the catalytic chamber. So we need to remove that heat. So the sulfur 6 oxide that has been formed is taken back into the heat exchanger where cooling occurs. This tells you that the heat exchanger has two functions. It is used for heating to increase the temperatures, but it's also used for cooling to reduce the temperatures. After it has been cooled, it's taken to the absorption tower. Remember, we are in this section now. When it's taken to the absorption tower, sulfur 6 oxide is dissolved in water. Is not dissolved in water. There's a reason why we do not do that, because the reaction is very exothermic. So it's going to cause the production of sulfuric 6 acid, which occurs in fumes or in vapors, which can be very, very, very harmful. So what happens, instead of dissolving it in water, we dissolve it first in sulfuric acid, and it's concentrated sulfuric acid to form oleum. Oleum is this compound here. Then the oleum now is taken to the diluter. We are here where now it's diluted with water. So when it's diluted with water, it forms sulfuric 6 acid that we want at the end of the day. And scrubbing is usually done in this reaction because you know that sulfur 4 oxide is one of the major pollutants, and also we know sulfur 6 oxide that is being produced is also another pollutant. So this reaction is reversible. So sulfur 4 oxide is usually converted to sulfur 6 oxide, but some of them can pass into the atmosphere. So that is the reason why scrubbing is done in this reaction. And scrubbing is the introduction of a base or bases, and the most common that is used is calcium hydroxide. So when calcium hydroxide is introduced, sulfur 4 oxide reacts with calcium hydroxide to form calcium sulfate and water. Remember, we mentioned this in the reactions of sulfur 4 oxide. So it forms a sulfite and water. And then in certain cases, filters are also installed to remove any traces of acid spray or mist from the exhaust gases. The unreacted gases, that is sulfur 4 and sulfur 6, may be recycled within the process. So this brings us to the end. That's how contact process occurs. You can go back to the video, pause in the places you didn't understand or I was fast, and check those reactions slowly by slowly. It's a very commonly tested question in paper 2, so make sure you're able to answer those questions comfortably. So see you in the next lesson as we go to most of the reactions of this acid that we have just produced. See you then.